millisecond pulsars are low luminosity, and there are none yet known within the centre of the bulge of the galaxy. And of course the search is going on, will be going on with SKA for them. So there are expected to be a few thousand such pulsars. You can calculate that on the basis of the stellar population. There's going to be no shortage of them once you can reach the detection limit. And then some of those will be very suitable for making this accurate timing. You know, the ones that are not binary orbits. So this is going to be a test that will be crucial for testing this idea. Here's the level that we expect. You can translate that timing amplitude into a strain and then compare it with. So we would basically, for 10 to the minus 22 electron volts, we're expecting a signal up here, which is, it's already really detectable with this pulsar timing array, but they don't have pulsars at the centre. So the SKA is needed, and it's certainly well within detectability of the SKA new radio, I think, which you're involved with. 5 minutes, is that what? Oh dear. All right, well look, we also now think, in addition to this 10 to the minus 22 eV axion that seems to work well on galactic scales, that there's good evidence for compact dark matter of the same form on 10 to the minus 18 electron volts inside these globular clusters. And these are the objects that don't have dark matter on large scales, so they're very much smaller than the de Broglie wavelength of the 10 to the minus 22 electron volt that we've been deriving for the dark matter. But there could be a small fraction of, this discrete axiverse picture you expect, perhaps separated by a few orders of magnitude, higher or lower mass, in this case higher mass axion, would have then the ability to condense inside such a remarkably dense object. It wouldn't be able to avoid it, basically, because the gravitational field of these stellar objects is so deep that the de Broglie wavelength structure on about a parsec scale should be detectable if there is a fraction of all the dark matter, a small fraction at least, in a higher mass axion. So this is the This is the idea here, that you can then constrain using these. So I should say that increasingly masses of about 1,000 solar masses have been found inside these globular clusters at the centre, for which there's no real good explanation, because they don't, obviously, it seems they don't accrete any mass, so they're not likely to be black holes. Well, that's the obvious candidate. But so there's a lot of debate about what they might be, and we would say, well, they can be quite compact solitons of this kind of dark matter. So this is now very important to try and resolve that central area of these globular clusters, to see if the mass profile of these 1,000 solar mass objects is extended, or is it just a point mass? That, of course, then immediately tells you. That would really help clarify whether there is a soliton matter, and that then would be a wonderful evidence for the axiverse, because you would at least have two scales, one for the general dark matter and one for these objects that are otherwise hard to explain in here. So that is the basic generic prediction of string theory, and then we would all relax. So anyway, we come into this now. We have a paper there with these guys, and we're already with that one. There's this funny object just discovered recently that lacks dark matter, so-called. It's similar to the dwarf spheroidals, but it's a bit more luminous. The velocity dispersion is only 3 kilometers a second as a function of radius. And there's a very similar object that wasn't mentioned for some reason in this paper, but created 2, where that also has this minimal mass. So it seems that there's a minimum velocity dispersion for some very extended looking dwarf spheroidal galaxies. These are large, up to 3 kiloparsecs in size. And so that really makes sense with our extended soliton idea. In fact, the profile of this very lowest mass object with this very large core is able to reproduce precisely the mass profile that they derive analytically for this kind of object. So here it is here. So we would say that such very extended, large and very low mass objects are naturally explained as the limiting lowest mass cases in our simulations, that being the lowest mass object. So that limit, of course, is sensitive to the axion mass, so it does hang together again that these new objects that have been discovered. And so the reason why you think, well, there's maybe not much dark matter in there is because the density of this dark matter is extremely low. But nevertheless, the profile fits very well this kind of data. So this is something that is also hanging together. Now, more exciting than all of that is this anomalous hydrogen absorption, now detected at redshift 17, actually between 15 and 20. And that's proving to be a real headache for the standard CDM picture, because even if all the diffuse gas in the CDM context was cooled down to the minimum kinetic temperature at that time, which is 7 Kelvin, it wouldn't provide enough absorption to explain this dip. This dip is about a 20% absorption of the CMB, if I understood what they actually measured. Right, so it's about half a Kelvin compared with 2.73 Kelvin, the temperature of the background.
Tom, what is a cosmic dawn?
The cosmic dawn.
Dawn, sorry.
Yeah, is please get that right, because cosmic dawn is something that you can find in the supermarket.
I know what it is, but yeah.
So it is, of course, the interesting, intriguing aspect of this is that the location in redshift of this feature has been quite well predicted by CDM. So it corresponds to an era when small stars would first form out of those little mini halos that we saw in the filaments, and they would then help the gas, the spin temperature, which is what's being measured here, couple with the kinetic motion of the gas, which is low temperature, it's less than the CMB, it's only 7 Kelvin. So if you say that that process is 100% efficient, then you can apparently produce half of this absorption at approximately the right time. And the reason it's called the cosmic dawn, has been called in advance of this detection, is just that those first stars are expected to form in CDM. Now in this wave dark matter picture, you notice that our galaxies form late. We don't have this early population of stars. And the difference is that we have all these dense, cold filaments. So we can write an expression down. There's nothing like the one that is relied on to interpret this in the context of CDM. It's the failure of this standard expression here to reach this depth that has caused the problems with CDM, and that's why there's been discussion suddenly of the silk type mechanism where perhaps there's a new relationship, the scattering of gas could occur with the dark matter, and the dark matter being very cold, colder than this, could then reduce the temperature of this gas further, lower the spin temperature, and bring down and enhance the absorption. The colder the gas, the more absorption there is, of course. Right? If the gas was the same temperature, you wouldn't notice it, it would just look like uniform surface brightness, but it clearly isn't. So that invoking to rescue CDM, this new force, apparently is problematic because all the experiments that were looking for fifth forces have put very tight constraints on such couplings. And so we, within only a week of this paper coming out, there's Barkana and others have written that, you know, in fact, that idea that they invoked using Joe Silk's method is now it doesn't work, because it would contradict other very stringent constraints. So maybe the filaments might do it. This was my thought. Our filaments develop at the same time from very smooth beginnings. They are incredibly high density, and the gas will be attracted with that, and first will heat and then cool. So this is an example of a simulation by a guy called Tom Toombs, I should have written that here, in Durham, who made what is really the only still very high resolution supercomputing calculation of how a filament would form and cool. This is in the context of warm dark matter. Warm dark matter shares similar characteristics as wave dark matter, because it doesn't have solitons and all that wave structure, but it is lacking small scale power, and therefore there will be no small galaxies. It has that advantage. The disadvantage is that to match the size of the cores locally, they will form no galaxies at all. This is the catch-22 situation with warm. So warm dark matter is not favoured because it is contradicting local data. But nevertheless, if you were to ask what happens to gas that cools in a smooth dark matter filament, this is a very good calculation of it. And it's just like our case, we have these smooth early filaments. The majority of the gas falls into these filaments because of the gravity of the dominant dark matter, and is compressed. And its temperature is high as it falls in because of the compression. Just like when the wind blows from the south here, right? It goes down the mountain, at least in our valley, and it heats. It's the same thing, the gas is heated. But then the densities reached are so high that molecules can form, and molecules then radiate hydrogen molecules and other things like three-body molecules, HD, deuterated hydrogen. They have radiation channels that can remove some of the energy quite efficiently, in fact. You only need trace amounts of that to cool these things very effectively. So this is what seems to be going on. And here in Toombs' calculation, you can see that the temperature, this is temperature, sorry, here in Kelvin. It's missing on the side there. And it reaches, it's reduced to around about 100 Kelvin or a little bit more in his simulations as he runs it to that point, but he's not including all the other cooling, only the molecular cooling. So the density is very, very high. So most of the gas is in these filaments, and they can be very cold. So you can bring down the spin temperature this way, just through collisional de-excitation of the 21 centimeter transition. You will then practically match the kinetic temperature. And so you can bring that down. And then we have an expression like this. This is our equivalent expression in the context of self-cooling filaments, where no stars are needed, no bath of early stars like CDM to couple it. This is just molecular, a slight extrapolation of the molecular cooling. And we can say that for example, a spin temperature of 40K at the observed redshift, the optical depth of the line, the level of absorption, is quite modest for high density gas. So these will be filaments of a parsec in thickness, where the gas density is around 10 to the 5 hydrogen atoms per centimeter cube. Quite reasonable numbers. These are very reasonable numbers when you look at this here. See, these gas densities 10 to the 5. The scale of these filaments is 1 parsec in this simulation by Toombs. So we are just basically adopting these numbers and finding that we can that then satisfies the 20% absorption, I should say, the choice of these numbers. So basically what will happen is that in this context, if this idea is right, a higher angular resolution, when data is taken that's not as low resolution as this, this line should break up into a very fine series of very deep lines, going far below here, almost to the base. And they would occupy only a small 20% fraction of the volume. So that's very very straightforward explanation. I mean, I have to double check these numbers because we've only just really got to this point in the last couple of days. So there we go. I believe that this kind of cooling mechanism makes so much sense compared to invoking new forces. You just have to be comfortable with the idea of smooth filaments and therefore wave dark matter. Warm dark matter, say, can do it, but it runs into other trouble. And this also then can provide an explanation for these globular clusters, because they would then form as the first objects when that gas cools in a top-down way. I don't have time to go into that, but you can form them quite readily in that way. And they would not have large-scale dark matter. So the ages of these clusters are, some of these clusters are as old as 13.5 gigayears. Now that exactly matches this redshift here at the end of this period of cosmic dawn. So you know what you want to do then is convert this cold hydrogen. It should have some sink, or it should be heated by formation of something. Stars would be the best idea, because then they both heat and consume the hydrogen, form out of the hydrogen. And that then would mark the transition between smooth filaments and the formation of the first massive stellar objects, which we know are globular clusters, must be, because their ages are 13.5 gigayears, and that actually coincides with the redshift of 15, that number. The universe is thought to be 13 point, I don't know what your latest value is. That's the
0.8.
13.8, right, so 0.4 gigayears. That is when this is, you see that? Almost, right? 300 million years. Okay, so within 0.1 of a gigayear, the coincidence between the ages of those oldest completely metal poor globulars coincides with the end of this era. And they can form those clusters in the top-down collapse of these cool hydrogen filaments. I believe. I mean, there is still slightly to be worked on. Admit. But they can hang together. And then they would not, you see, one question to ask independently of all this, the final question is, why is it these globular clusters don't have dark matter? Why is it their mass profiles drop, as I showed before, the velocities, right? So they don't have dark matter. How could it be that something that old didn't accrete some cold particles? If you like these cold particles, it should have occurred. They're very massive. There would be no reason why not. The motion of those particles is very low at that time. They're not in bound structures with high dispersion. They're in best tiny structures. So the lack of dark matter tells you at that time that the dark matter is not heavy particles or even black holes. That would be worse. But instead, wave dark matter works because it will compress these filaments. The gas can cool in it, but the filament dark matter can't collapse with it. It does collapse later into galaxies, so it's always growing, but it can't collapse on small scales because the de Broglie wavelength is much bigger than the scale of these dense star clusters, which are only a few parsecs in scale. The de Broglie wavelength you would associate would be 1,000 parsecs. So you expect them not to have dark matter in this picture. So the whole thing can hang together very coherently, I think. We can explain the properties of the lowest mass galaxies, the formation of globular clusters, the absence of their dark matter. And this edges result can make quite straight. You don't have to have very cold gas, a few tens of Kelvin. It seems physically quite reasonable, this combination of factors. So that's it.
Thank you very much. Questions?
Yes, I have. Okay, so I'm fully ignorant of this, but just try to rephrase what you say. So you have bosons, very cold bosons, okay, inside a box, okay, the box is the universe,
Yes.
and then you run, the non-relativistic quantum solutions, okay, including the gravitatorial potential, okay.
Yeah, and we assume the bosons share the same wave function, that they're coherent.
Yes, exactly, and they are highly interacting. Okay, so they just overlap, so they are not independent. Let's say.
Well, there's no scattering involved between them. We just say only gravity is involved.
Only gravity.
That's why we have only this one free parameter. Otherwise, you'd have to invent some cross-section of gravity. I think, what we're thinking is that on astronomical scales, we're not worried about microscopic interactions.
Okay, so I have two very basic questions. So the first one is that you need to have some kind of boundary condition, right?
Well, you start from a power spectrum of the inflation or whatever provides that's been measured by the C and B. So that gives you your perturbations that then grow under their own gravity. So it's the self-gravity of this perturbed Bose condensate that leads to condensed structures, including filaments and galaxies. That's how they develop out of this here. It is actually a very straightforward calculation. You use that Schrödinger-Poisson equation,
Yeah.
apply it to the whole field, and out of these very smooth beginnings, with very little small-scale structure, only large-scale structure, because you suppressed it with the uncertainty principle, these structures form. And you end up with an interference pattern where you have, objects that are self-bound with these equilibrium configurations that include all this rich structure.
How much time goes by between those pictures?
That's a good question. This is around a redshift of 50. I know that we started then. And this is around redshift of 10 when the first galaxies formed. So these are in the era of the so-called cosmic dawn. Although we wouldn't have any dawn in this picture, you see. We would be star-free, so it wouldn't be like the sunrise. So then it would have to be sort of...
Okay, so the second part of the question is, what about the entropy? Is the entropy of the final system larger than the first one? Because, it looks like you're getting more ordered things, so in such a way I'm surprised that at the end you get with a system which seems to be
Well, this is a general feature of structure formation, that despite this order that is formed on small scales, overall the entropy is rising. Okay, so that has been thought through. And
you can compute it and see.
Yes. Don't need to worry about it.
Okay, because for me, I can understand the thing that things get cooled down. Okay, the fermion matter or whatever, when it interacts with something which is cooler, it just cool down. But how can you explain that it gets warm up again? This is against thermodynamics, right?
What warms up in the cores of these?
When you presented it, maybe I misunderstood it, but on slide number 81, that one. So I can understand that, okay, things get cooled down, but I cannot understand how they warm up again.
Well, there would have to be some injection of heat from stars, or something that, so initially, this is the earlier time, right, and these filaments would form in this picture. Then the gas would keep cooling, and at some point, determined by some sensible time scale, maybe the formation of these globular